In teaching about plate tectonics, one of the problems that we've had is getting students to understand plate motions on a sphere and to actually do it in a quantitative way. We've always used maps, and we have great maps that we can use that show the magnetic anomalies, the age of the oceans, and from those you can calculate plate motions, poles of rotation, and all of the tools we want to do. The problem is the map itself, the map projection, complicates things. It adds a whole level of additional mathematical work the students need to do to get at the primary questions. That's not a problem on a globe because the globe reflects the true shape of the Earth. And so in working with real-world globes, we were able to put together a new globe that shows the magnetic lineations, the age of the oceans, shows the bathymetry of the ocean, shows topography on land, that we can use to determine quantitative aspects of plate tectonics. Rates of spreading, areas of plates, poles of rotation, all of the different features that students use when they're analyzing plate motions, and the students can see it directly without having to go through a series of mathematical exercises in order to make it work. So what we'll do today is actually show some of the activities we can do with these globes.
One of the other things you can do with the globe is just simply look at patterns of magnetic anomalies. For example, if you look at the Atlantic Ocean, we've got lots of magnetic anomalies in the north, lots in the south, and a gap between them. This is not a measurement gap. This is the fact that we have a very difficult time actually measuring magnetic anomalies near the equator in the Atlantic Ocean. Of course, if we simply look on the other side of South America, we see that we can measure magnetic anomalies over here in the Pacific. So what's the difference? Well, this comes down to a physics problem, and it's related to magnetism. So we have our mid-ocean ridge is basically north-south, and we're spreading this way, so we're forming materials that are magnetized in a north-south direction. What this means, because of the way the magnetic field in the Earth works, is the magnetic field doesn't ever come out of the Earth. So when we go and try to measure whether the magnetic field is stronger or weaker in near the equator, we can't actually tell here because of the way magnetism works. And then if we go over to the Pacific Ocean, because this spreading ridge is oriented east-west, and so the magnetized crust is oriented east-west as well, then this short section of crust does have magnetic field that comes out of the Earth, which we can measure as a positive or negative anomaly. So that's why we can measure them over here in the Pacific, but over here in the Atlantic, we can't measure those magnetic anomalies anymore.